For some, the sound of a singing kettle is comforting. For others, it's a mystery. That rising hum, the gentle whistle, the final, triumphant shriek as water approaches its boiling point. It's a familiar soundtrack in kitchens worldwide, yet few of us stop to consider why it happens. What hidden physics are at play, orchestrating this daily symphony of heat and water? It's more than just simple bubbling. The sounds we hear are a complex interplay of pressure, temperature, and tiny, invisible forces. From the quietest whisper to the loudest roar, your kettle is telling a story, a narrative of energy transfer and phase changes unfolding right before your eyes, or rather, your ears. The journey begins quietly. As the heating element warms the water at the bottom of the kettle, the first thing to form isn't a large, robust bubble, but rather microscopic pockets of water vapor. These are tiny, embryonic bubbles, clinging to imperfections on the kettle's surface, like microscopic mountains providing nucleation sites. At this early stage, the water above these nascent bubbles is still relatively cool. When these tiny vapor bubbles detach and rise, they quickly encounter cooler water. This causes them to instantly collapse, imploding with a barely audible pop. It's a rapid, violent process, invisible to the naked eye, but crucial to the kettle's first whispers. This constant formation and collapse of tiny bubbles creates a gentle, low-frequency rumble. Think of it as the kettle clearing its throat, preparing for the main performance. This rumble is the sound of thousands, even millions, of these microscopic implosions happening simultaneously, a chaotic yet harmonic orchestra. As the water heats further, the bubbles grow larger and survive longer. They travel higher into the water column before collapsing. The frequency of these implosions starts to increase, and with it, the pitch of the sound we hear begins to rise. This is where the singing truly begins, a transition from a low rumble to a distinct hum. The kettle itself acts as a resonator. Just like a musical instrument, the kettle's shape and material amplify certain frequencies. The vibrations from the collapsing bubbles are transferred to the kettle walls, which then vibrate at their own natural resonant frequencies, creating the distinctive hum we associate with a heating kettle. This phenomenon isn't unique to kettles. Think about blowing across the top of a glass bottle. The air inside resonates at a particular frequency, producing a tone. The same principle applies here, but instead of blowing air, it's the chaotic energy of collapsing bubbles driving the resonance. As the water temperature approaches boiling, the upper layers of water also become hot enough to sustain these vapor bubbles. They no longer collapse immediately upon rising. Instead, they grow, merge, and travel all the way to the surface, where they finally burst, releasing steam. This transition marks the peak of the kettle's song. The continuous, rapid formation and escape of large bubbles create a sustained, higher-pitched whistle or shriek. It's the kettle's way of announcing its readiness, a clear signal that the water has reached its boiling point and is ready for your tea or coffee. But what about the kettle's silence at full boil? It's a curious reversal. After reaching its loudest point, the sound often diminishes, settling into a more consistent, less melodic roar. This isn't a malfunction. It's another fascinating aspect of the physics at play. Once all the water in the kettle reaches 100 degrees Celsius or 212 degrees Fahrenheit, the temperature difference between the bottom and the top of the kettle largely disappears. The conditions that cause the bubbles to collapse in the cooler water are gone. The water is uniformly hot. Now, the bubbles no longer form and collapse in the middle of the water column. They form at the bottom, grow, and rise directly to the surface without encountering significantly cooler water. This eliminates the rapid implosions that generated the higher-pitched singing sound. Instead, what you hear is the sound of larger, more stable steam bubbles forming and bursting at the surface, along with the turbulent movement of the boiling water itself. It's a deeper, more consistent rumble, a powerful roar rather than a melodic song. The symphony has reached its climax and is now sustaining a powerful chord. This entire process, from the first whisper to the final roar, usually takes just a few minutes, depending on your kettle and the volume of water. But within that short span, we witness a complete transformation of energy from electrical to thermal, and finally, into the kinetic energy of moving water and vapor, expressed as sound. The design of the kettle also plays a role in how pronounced its singing is. Older stovetop kettles with specific whistle mechanisms are designed to amplify the sound of escaping steam, forcing it through a narrow opening to create a piercing shriek. Electric kettles, while often having a less dramatic sound profile, still follow the same fundamental physics. Their internal heating elements, and often larger water volumes, simply create a slightly different acoustic experience. But the underlying bubble dynamics remain constant. So the next time you put the kettle on, take a moment to really listen. Hear the subtle shifts, the rising pitch, the eventual crescendo, and the settling roar. It's not just water heating, it's a live physics experiment unfolding in your kitchen, a daily reminder of the incredible forces shaping our world. This intricate dance of bubbles and resonance isn't just about making tea. It's a microcosm of thermodynamics, fluid dynamics, and acoustics, all wrapped up in one familiar appliance. It shows us that even the simplest objects hold layers of scientific wonder, waiting to be discovered. From the humble kettle to the vast ocean, the principles of boiling and cavitation, the rapid formation and collapse of vapor bubbles, are fundamental. They influence everything from ship propellers creating destructive forces to the way certain industrial processes are designed. Understanding why your kettle sings doesn't just satisfy curiosity. It opens a window into a deeper appreciation for the physical world around us. It transforms an everyday occurrence into an opportunity for scientific insight, making the mundane truly magical. So the next time you hear that familiar tune, remember the journey those water molecules are on. From silent slumber to vaporous song, your kettle is conducting a symphony of physics, right there on your stovetop or countertop. It's a testament to how even the most ordinary objects in our homes hold extraordinary stories, just waiting for us to pay attention and uncover their secrets. What other everyday sounds hold hidden scientific marvels?